bit unfair, but nevertheless they did. One of the other big retail providers, CenturyLink. And you can see the list as well as I can, but folk are dropping. Who's growing? Well, Amazon is growing, Vietnam is growing, but the other areas of growth are not frenetically high. They're not really high. So it's an interesting kind of view of the fib count, but let's move on a bit now, because I actually want to show a different metric. This is the amount of address space in total, the span. And now you see a completely different story, that in essence the great boom and bust didn't mean anything. The consumer market did, but the onset of address exhaustion really did impact the way we build networks. Because at that point, what we were advertising was close to the real thing. There was a minor rush to get addresses in that period before Ayanna died and a bit after, but then as it plateaued off, there's been no new addresses in the routing system. What about over here? US Department of Defense, enough said. The other thing you also notice is there's an awful lot of noise in addressing span, an awful lot. Because a whole bunch of peers of route views and RIS don't actually send their complete tables, they just send subviews. So the major thing is default running default free, the rest is kind of little bits of subsets. So an entirely different view of where growth is. Let's advance the slide forward. Please advance the slide forward. Help. Someone press forward. I'm trying. There we go. So I'm going to look at 2023. I'll go backwards by one to see, this is the one. This is the first slide I've ever shown of this dimension. This is no longer up and to the right, it's down and to the right. This is, yes, the S word, saturation. Have we reached that point where the market is actually fully saturated? Because if you look at the amount of address span across 2023, it's not growing, it fell. And it fell a lot. And the only reason why it didn't fall sort of monotonically is dear old Amazon, who is still going with a model that says every customer needs a new address, God knows why, decided to bump in a whole bunch of addresses into their plant. But it's falling. The address space is actually falling in terms of advertised address span. Now we get to this slide. If we take the 0 point at the start of the year, the red line is the total size of unadvertised addresses. And over the year, it grew by 18 million addresses. A net of 18 million addresses got taken out of the routing system and actually stashed into somewhere else that we can't see. And you see the blue line, which is the advertised space, also, if you will, fell by the same amount. Amazon is there in the middle with that jump function. But basically, we are removing addresses, not using more. The unadvertised pool is not falling, it is growing. The RIRs, nothing happened. They're exhausted. There's nothing left. There's nothing new to give out. So the green line, which is RIR allocations, is basically steady across the entire 12 months. So no net recovery, 18 million addresses got withdrawn. Bigger view kind of suggests that that thing started, the falling of unadvertised, at around 2020, in the middle of COVID, or the early parts. And at that point, the IPv4 network simply stopped growing and started to shrink, and shrink a lot. The big step function there in 2021, DoD/8s, they just decided to advertise some stuff that had never been advertised before, not really important. Who's pulling addresses out? Well, we mentioned SprintLink, China, Lucent, AT&T, relatively big. There's our friends in Turkey. Akamai, one of the hyperscalers, is actually advertising fewer addresses, as is Google, as is Comcast. They're not growing in terms of addresses. In terms of addresses, they're getting smaller. You see on the right, the folk are actually growing. Need I say more? You can read as well as I can. There, you've had enough time. Hope you studied it. The summary of what I said, things are slowing down. We could have peaked. We could have actually reached a point where the V4 network has got to about as big as it's going to get. The advertised span has actually declined slowly over the year, and we may have got to that point where the V4 network is as big as it'll ever get. The numbers certainly seem to say so. Whether the behaviour of the industry says it as well, But we seem to have stopped at about 1 million fib entries, and we seem to have stopped at around 3 billion or so advertised addresses. Okay, so you're all meant to be running V6, aren't you? Yes, Jeff, we are. We're all meant to be running V6. And here you see the first kind of, oh yes, well it's right, it's up and to the right, it's strongly exponential. V6 is taking off, really, isn't it? Again, let's look behind that number, because it looks good, but it's just quite not what you think. There's 2023 compared to the long trend. Long trend, 2023. Not exactly vertical, not exactly highly sloped. It's not going down, it's not, but the number of fib entries is growing slightly. Growth is not momentous, and in fact, tailing off in the last third of the year, it's actually plateauing out. Again, the S word, saturation. Because what it seems to be is, there were some step functions in Vietnam and one in Hong Kong, but beyond that, the amount of growth, look at those last 2 months. The amount of new activity and new deployment in V6 is actually trailing off. So what's fueling that growth? More consumers, more customers, or something else? For a long time, V6 was never used for traffic engineering. For a long time, V6 was a disused orphan child of V4. No one gave it any attention, and whether it actually worked or failed made no difference because, happy eyeballs. As long as V4 worked, the network was working. But in fact, since about 2017, folks started taking V6 slightly more seriously and started to use it for traffic engineering. How do we know that? Because you started advertising /48s as more specifics. So all of a sudden, you're trying to balance the traffic in V6 over more specifics. And now the number of more specifics in V6 is close to 60% of the entire block of, routing. So it's just littered with /48s. How sustainable is this? How many /48s are there in V6? Well, a lot, a huge amount. More than your router could possibly ever cope for in the next decade or two? Well, yes. This is crazy. You can't put a cap on this if that's the way you want to go, because there are more 48s than you can possibly handle. But V6 is kind of going there, pumping the network full of /48s. Here's a different picture. Advertised address span. Just to remind you, let's flip the charts again. Number of routing entries, up and to the right. Address span, more constrained. The real growth factors are actually much, 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 much lower. They're gentler. They actually reflect a much more reluctant industry to actually embrace V6. And look at 2023 in advertised addresses. Flat. Well, I wouldn't say completely flat, but the growth is really, really small. There's not an awful lot of activity in expanding that network in terms of its address span. What we have at the start of the year is largely what we got at the end of the year. So we grew by 30,000 entries, yay, but the growth was really in /48s. It wasn't in more addresses, more connectivity. 1.6% of growth. The world population grew by 3%. So in actual fact, it's losing pace. So it's much, much lower than even the previous 4 or 5 years. Again, the S word. So let's go to some projections. If you're buying a piece of equipment now, you've got about, 5 years of useful life out there in the field. How big do you need to get 5 years of growth in the size of the routing table? V4, this is the first time the numbers, just a straight mathematical model, using an order 2 polynomial, tend to suggest we have peaked at 1 million, slightly under. And the numbers suggest it's going down. Now, these are just numbers. What you do with your customers and your routers, I have no idea. And it may go either way. But the last 5 years' numbers suggest that the growth not only is going down, but it's going to go negative, and the peaking point is around about now, give or take a year or two, and then the numbers suggest it will actually start to fall. The folk who are withdrawing will outnumber the folk who are growing. Never done that graph before with a downward. Never. It's always been, it's linear. The linear slope is low. Now it's kind of, no, it tipped over. V6, a few years ago, the exponential trend looked pretty solid. Now it doesn't. Even a polynomial is flattening out to look a lot like linear. The best projection is kind of a linear growth model that is very, very gentle growth in V6. So in actual fact, all of these trends tend to suggest that the actual market demand for this stuff is close to peaking, and instead of growing in the address space, we're growing in different areas. Hint, it's the namespace. So, it looks like we are plateauing out even in 6. 1 year from now, you will devote as much space in your high-speed memory to V4 and V6 because V6 tables are 4 times bigger in general. So at that point, V6 will have got to 25% of V4. And the real good news in all of this, BGP will see us to our collective death. There is no reason to suspect that BGP is under astronomical pressure. You don't need to change anything at all. BGP is coping and will look like it will continue to cope across all of these numbers. But it's not quite how big it is, it's also how much thrashing, because BGP is a distance vector protocol, and that's one of the least efficient protocols known to man. It works really well, but it's highly inefficient. It works by exhaustive search. And that exhaustive search and a bigger network can get phenomenally difficult. The yellow line, the growth of the network in V4. The blue line, from where I sit in my router at the edge of my network, it's a me picture, is the number of updates I see per day. In a standard distance vector routing protocol, if noise was kind of randomly distributed, the blue line would rise either equal to the yellow line or even at a greater rate as a square, because it's distance vector. It didn't. It's actually risen gently, and in the last year or so, the number of updates has actually plateaued out. It's actually now quite slight at around, 200,000 updates a day from where I sit. What's the problem, guys? What's wrong with updates? Why do you limit them? And look at the bottom line, which is the number of withdrawals. Apart from a hiccup, at the start of 2023, the number of withdrawals has been astonishingly stable. I want to withdraw a route. No, it's not your turn. Wait. I'm only allowed 10,000 withdrawals a day and you're not in the quota. Somehow, some way, the dynamic behaviour of this routing protocol is limiting itself, even though there's no agreement with operators, there's no overlying control factor, the system is actually capped. It's a self-limiting system without any governing constraint being applied externally. One of today's modern technical miracles. God knows how you do it, I certainly don't. So surprisingly stable, whoopee-doo. The number of unstable prefixes, the naughty corner down the end there, phenomenally stable. I want to update my prefix. No, you're not allowed, because only these number of prefixes, only this set are allowed to update. So most of the network for the last 20 odd years does nothing in BGP, just nothing. You announce a network, yawn, nothing changes. Phenomenally stable. Instability is highly concentrated in a bunch of folk who don't know what they're doing. And those folk are incredibly naughty. Yeah, the two leaving the room. Incredibly naughty, and everything else is actually phenomenally stable. This is great because this is what keeps BGP alive. So slowly increasing, almost imperceptibly. V4 convergence times, if you change your routing within approximately 49 seconds, which is 2 MRI intervals, 2 minimum route advertising intervals, the world will see it. And that was true back in 2014, it is true today. The network has grown phenomenally, but it's the same timer. Because the network is not getting less efficient, performance is not getting worse. Performance is constant, because the underlying topology, oddly enough, is roughly constant. This is, again, amazing. There's nothing deliberate, it's nothing in the protocol. The way you've built this network has these properties. So, highly stable. V6 updates, completely wrong. You guys don't know what you're doing, or you just don't care, or you're not looking. or all three, because the number of updates is roughly equal to the size of the table, the number of withdrawals is growing. This stuff is all over the floor. It is not contained. Whatever you're doing in V4, you're not doing in V6. You're just not. You're just not looking. So these things that we're seeing in V4, I think are the result, you actually give it some time and attention. It's what you're getting paid to do. No one's paying you to look after V6. You don't care. It works like crap. And it is crap. Growth trajectory is high. Unstable prefix is growing. So it's not just the naughty corner, it's the naughty half the room. And as the room gets bigger, the naughty half the room gets bigger. They just keep on growing. You're not looking, you don't care. So you say to everyone, you must run V6. Why? Because we're not looking after it and performance is lousy. Okay, great deal. Why do you hate your customers? Run V4, it actually works better in this age. Convergence performance was horrible for years. All those overlays, let's run V6 over tunnels, bad idea. It's slowly getting to a convergence performance in the last year that looks a lot like V4, but it's taken almost 20 years to get to that point. So that's kind of good. Updates. This is the cumulative distribution. If everyone did updates, it'd be right on the diagonal. If only a few very, very naughty people did almost all the updates, green, V6, only a small number of folk would actually be contributing to the entire set of noise in V6. And that's what's going on, that V6, a small number of people are pathologically unstable. And they just pound the entire network with a huge number of updates. If they stopped, you might actually find the network is far more stable. But yes, at the moment, 2 ASs, 50% of the V6 updates, we thank you very much. Conclusions, because I'm running out of time. BGP is fine. BGP is fine. If you want to develop a new interdomain routing protocol, feel free, but no one's interested in what you're doing. That expansion is over. The driver of growth is over. Everything's moving up in the protocol stack. Infrastructure is now stable, moribund, and saturated. The world is in the application world. The world is in CDNs and applications. The underlying plant in the addressing and routing factory is kind of, we're built enough. Whatever it is we're built enough of, it's not growing. But there are a few things you need to know, Optus, and you need to know the size of your fib table, Optus, and you need to understand that when it gets over 1 million, Optus, one of these things might trip over the max prefix length limit, and you might find your national network is completely isolated, Optus, from your engineering support group in another country. Oops, Optus. It was just sitting there waiting for 1 million, and 1 million came and it went bing, and it was kind of, the entire network was cut off. A few million Australians couldn't even have the emergency, what we do, the 000 number. Thank you indeed. Look at that number. Don't ignore it. It's an important number. And by the way, when you exceed it, don't shut down the session. That's really dumb. Freeze your fib table and alarm like crazy, but do not shut down the session. Because, Optus, it will happen to you and your CEO will have to fall on her collective sword, as I think the CTO and some others. Because, you know, that's an important line. Understand the limit and understand what happens when you exceed it. Optus, other than poking fun at them, most others have actually survived this. Do have a look at your settings in the fib table. It is important. It is important because they are growing. And don't forget, V6 is 4 times bigger than V4. Default routes can be really, really, really helpful. You don't have to carry all the tables unless you feel like doing it and, you know, have nothing to do on a Wednesday afternoon. Run default. And quite frankly, there are a number of vendors experimenting with various forms of fib compression. Interesting, although one of them has just been bought by HP, so who knows what will happen to that. And hot caching also gets you out of the bind of having to do the world's most expensive memory to hold 1 million 32-bit entries and 250,000 128-bit entries, all to handle traffic that only goes to 50 destinations if you're lucky. If you did hot caching in those fib cards, you could get away with about, well, 50 bytes of memory if you did hot caching. So you don't have to solve everybody's problem at absolute line rate. You can be selective and that will be cheaper. So, you know, if you're doing that, that's a really good thing. I've run out of time. Is there any questions? Thank you.
Thank you very much, Jeff. Do you have any question? Maybe I can take one. Yes.
Cool.
Yes.
Oh, there is one. Sorry, Barry. I was running away.
Yeah, please state your name.
Barry Green with Shadow Server right now. So, Jeff, updates. What if we times 100 all on one day from 300 devices across the internet with BGP withdrawals as the sessions flap up and down?
What if you massively increase the updates from one source?
No, 300 sources.
And they all started chattering away with BGP updates.
Right. Up and down, up and down, up and down sessions, up and down, up and down, up and down. We have close to 400,000 BGP sessions out there because we're thinking so much about, oh, let's go assign our routes, but we're not doing anything to protect the sessions. And every now and then the bad guys are poking at it. So state actors understand how to do this.
You know, we occasionally put out advisories going, route flap damping is really good. And then the pendulum swings and we put out these sort of informal views going, route flap damping is a waste of everyone's time. What's the problem? And then you go, well, route flap damping is really good. And the real answer is, it depends on when you ask the question, whether route flap damping is good and protects us from things like this, or just an administrative waste of time that routes get put in a sin bin for no real reason. But there is route flap damping for situations exactly like that.
Right.
In the grander scheme of things, in today's world, I think we're relatively laissez-faire about routing. Route flap damping is too much work, I don't care. But that's today's view. Come back in 2 years' time, the pendulum will have swung. Must do route flap damping, you know, so yeah, we have the tools, but not everyone deploys it all of the time.
Yes.
Yeah, thank you.
Thank you very much.
Thank you very much.
So we have next up Doug Madry from Kentic. He will share some BGP incidents. Yeah, we have.
Hello. All right. Got the...
So you have a clicker and then you receive over there.
Okay.
And that's coming, guys.
All right. Thanks for having me. My name is Doug Midori. This is my talk, brief history of the internet's biggest BGP incidents. So let's get started. Whoops. Yeah. So this talk comes from some work I did with this organization called BTAG, which is an organization that represents the broadband providers in the United States who were responding to a request from the FCC, that's our federal agency that oversees communications in the US. They got an interest a couple of years ago into BGP and what they need to do to try to foster secure internet routing in the United States. And so I was part of this group of a couple dozen notable experts in BGP that wrote up this report. I recommend the report. The section I was mostly responsible for was looking at just the history of what, if someone were new to the topic, what would be the big incidents to be aware of to try to fill out the problem space. Because I had been writing about this for now going on about 15 years of writing these incidents. So I published on my own on the Kentic blog another version of this history. It got republished and translated, and so this talk is a mini version of that brief history, and I'll try to get through it today. So why don't we take a stroll through BGP incidents and understand why are these problematic? So we have either incidents that are disruptive to legitimate traffic, or incidents where there's some concern around traffic getting misdirected and perhaps intercepted, surveilled. And there's typically incidents fall into one of these two categories. People can make a case that some maybe fall into both. But when I try to talk about the problem space around BGP security, I try to explain that this is not like a one type thing. This is a constellation of problems and of a variety of different things we're trying to address here, and they sit on a spectrum of some that are kind of easy or embarrassingly mistakes that take out internet communications, on up to things that are legitimately difficult to solve. And when I first started working in this space and started writing about routing leaks and hijacks and those kind of incidents, we really weren't very good at solving anything on this spectrum. And I'm here to say that that's not the case anymore. There's been some progress. So let's start with routing leaks. So there's this RFC 7908 that defines a route leak as the propagation of routing announcements beyond their intended scope. It's a very elegant and concise synopsis of what is a routing leak. Now, in that RFC, it goes on to define, kind of create a taxonomy of a variety of different types of scenarios of route leaks. For me, I like to just use two buckets of things that are misoriginated, leaks that are misoriginations, and then adjacency leaks where you've got routes coming in from one side that are getting egressed out a way they shouldn't. The reason this is useful for me is because we have different mitigation strategies for these two different categories, and those are useful to me. So let's go through origin leaks. So this begins with an incident way back in April 1997, before my time in the industry, where there was a routing leak due to a software bug that caused a router to disaggregate all the routes in the routing table to /24s, announce these out to the internet, and obviously bad things ensue. The network was knocked offline. One thing that was unique about this in the state at this time, according to the folks that I know that were around then, is that this bug was so bad that once they isolated the problematic router, a lot of these announcements were still in circulation and required manual intervention to completely clear this out. So that's an issue we don't see so much anymore. But there have been a number of routing of origination leaks in the ensuing years. Although I would argue we don't see them so much anymore, and that's not by accident. But the list, the pantheon of big events here of Turk Telecom showed up in Jeff's slides a few minutes ago. We have this China Telecom leak that got a lot of people agitated in the US in 2010, a Telecom Malaysia leak. This graphic on the right is from a talk I gave in RIPE and Nanog about, 4 or 5 years ago, looking at just the propagation of the routes within a leak. We use the term like, 50,000 routes. Well, not all of them had the same amount of disruption. The supposition is that a bad route that propagates farther has the potential to do more damage, and those that don't go anywhere probably didn't do that much. And in this case, if we were to apply that analysis to some of these events, in this case, it was really a China-on-China incident. Those were the leaks that were the routes that were most affected. But so there's those are a couple of the origination leaks, and then we've got this kind of subcategory of leaked hijacks. And so these are things that are both a particle and a wave. They're intentional, but also accidental. And the most famous one is this Pakistan incident that I'm sure most people are aware of. But this is something that we continue to see ongoing even in the past year of routes that are intended to be blocking traffic locally that leak out. So what's interesting is to look at this incident with this particular 1/24 belonging to Twitter or X that suffered a couple of hijacks. One was during the aftermath of the military coup in Myanmar, here next door, where there was a crackdown on social media. The government ordered ISPs to drop traffic. One of those networks elected to do this via BGP, a lot like PTCL did to YouTube many years ago. Unfortunately, it leaked out, again, like the Pakistan example, and disrupted Twitter access in this region for a period of time. 1 year later, there was a similar incident where, again, in the aftermath of the Russian invasion of Ukraine, Russia had a crackdown on social media. One of the providers decided they were going to block Twitter by announcing the same /24, almost a year to the day. It also leaked out. So the circumstances were very similar, but the impact was very different. And what happened between these two incidents was that Twitter, X, they were still Twitter at the time, had created ROAs for all their routes. And that enabled other ASs to see that this hijack route that was coming out of Russia was illegitimate and blocked it, dropped it, and the traffic impact between these two is remarkably different. These are the types of successes that RPKI offers on a near daily basis that don't They weren't blogs, they don't get a lot of press, but this is what success looks like of just, we're trying to limit the bad routes, how they propagate. This doesn't help the folks in Myanmar and Russia in this case, but this is a system working. In the case of, now we move on to adjacency leaks. So here's a couple that are worth considering. So we had this main one leak. This main one is a big provider out of Nigeria, one of the largest international gateways on the west coast of Africa. Basically took routes from its peers and announced them to transit providers. It happened to be China Telecom, then passed this on to the wider internet, and there was a lot of, again, agitation around that. To their credit, they posted on social media within a couple hours, hey, this was our mistake, everybody settle down. And then, not even a year later, we had this Allegheny Tech leak where you had a small network. One of our providers was using a route optimizer, so that was creating a small set of more specifics that were intended to stay local, and through this leaked out onto the internet. What's interesting here is that the figure I have 29,000 routes. That's true. As far as how many routes were involved in the leak, it's really about 200 that were the ones that were problems, because those are the ones that were more specifics. The rest of them were just passed through, and those 200 were for content, just how this route optimizer was working. It was trying to optimize traffic to content providers. Cloudflare was one that was probably arguably the most impacted content provider here. What's interesting in that case is that it was Verizon at the time that carried us onto the rest of the internet. Had they been rejecting invalids, it probably wouldn't have been that big of a deal, but only because of the max prefix length violation that the route optimizer would have created. Because in this last bullet we see this is what the paths look like, and so the origins were intact. So any kind of origin-based mechanism is not going to do anything for you here. We have to have something else, and that's part of the motivation for ASPA, where ASs would register what are their transit relationships that would enable other ASs to look at AS paths and figure out where are things like value-free violations and be able to reject those routes. So that's part of the motivation for ASPA, or maybe it's the main motivation. But the other, I guess, lesson learned there was that if you're going to set a max prefix length, either have it match the route as routed, or don't use it is another option. So, as someone who's in the space, so you read a lot of the coverage of this, and sometimes you get these things of just like, oh, it's all, this is a disaster, and we have to replace BGP, and it's, what a mess this is. I kind of look at the other way. It's kind of remarkable. We have this one instance of one routing protocol governing the entire internet, and it actually works on a daily basis. We have, bridging gap protocol came from the Facebook outage. Who knows where they got that from? I was like, I swear that was not from me. But the question to ask yourself, in my opinion, again from looking at this for almost now 15 years, is when was the last debilitating BGP leak? Well, it's been a while. Maybe it was the Allegheny Tech one. That's it's approaching 5 years ago, and in internet time, that's a long time. This isn't by accident that this is getting better. Our fingers are not getting less fat. Mine certainly aren't. So let's talk about why maybe things are getting better. So one of the areas is RPKI, where we can measure some of the progress that we've made. And one of the big achievements was getting these DFC networks, the top tier 1 networks, to drop invalids. There's an enormous amount of downstream benefit that comes from them doing that. This graph comes from NIST. So this is, I mentioned FCC earlier, and NIST is another federal agency. We have a lot of them. And this one, they've got a team there that studies internet routing. And puts out a lot of great stuff. They have this website that publishes daily updated stats of a variety of types around RPKI. This graph, and I think it's easy to, maybe you can read the yellow is a little faint, but through time you can see the routing table have no ROA. They're unknown if they were to be evaluated, and then the green is valid. Well, there's an inflection point a few years ago where these lines were kind of flat, and now they're moving it's almost uncanny how straight these lines are, but they're about to cross. We're just weeks away from the majority of the v4 routing table being valid and having ROAs. For V6, that actually happened last year, so they're ahead of the game. And then there's a line of persistently invalid stuff that hugs the x-axis. And so 2 years ago, I had an insight. I work at a company that does a lot of NetFlow analysis. We have a lot of NetFlow data to look at. We also have a thing where we, upon ingest of records, we do a RPI evaluation of the destination IP. Would this have been gone? Would this traffic had gone to a route that was valid, invalid, whatever? And at the time, what was the insight was that at the time we only had about 1/3 of the BGP routes had ROAs. But when we looked at traffic, it was the majority. When I just threw all of our customer data into a big pot and looked, and so the idea was that we're making we've made more progress than we knew, and part of this comes from major eyeball networks doing RPI deployments and content providers. These networks may not account for the majority of routes, but they may account for a large share, or they do account for a large share, maybe a majority of the traffic that we pass. Now, if we take that, we update that to now, like in that graph from the previous slide where these things are about to cross, we're at like 50%, and now we're at like 2/3 of traffic in bits per second going to routes that are valid. So, and I even looked at tie routes. So in AFTAB session just a little while ago, yesterday, we looked at maybe 50% of the routes of the tie internet have ROAs. And I don't know, from our perspective, when I ran the numbers, we're seeing 80% bits per second going to tie routes with ROAs. So we actually maybe are making more progress here as well than we would have expected. But the ROAs are alone are useless if nobody's rejecting invalids. And so that's measuring who is rejecting invalids is a tricky thing, and there's been a number of attempts to try to answer this question. So my approach is the following. Is to take something like route views, a public BGP repository, take the whole table and evaluate all the routes, and then go back and look how many of the BGP sources saw each of the routes. So in this case, let me walk through this graph here. The x-axis is how many BGP sources. So RouteViews has got 300 and something. And there's a highly conserved peak around global routing in V4 and V6. And those that are not found or unknown, those without ROAs, look a lot like valids. So these are both not getting filtered. So those peaks look very similar. But if you look at those persistently invalid routes that we saw in the NIST graph, though that the distribution has shifted way to the left, meaning that the system is suppressing what it thinks are bad routes. Most of these are misconfigurations, but it's keeping these things from propagating around. And potentially, if these were disruptive, then this is again the system working. I challenge you to find an RPI invalid route that is globally routed. You can't find one that's even seen by 50% or more of BGP sources in RIPE-RIS or route views. It can't happen. And again, this is another way to measure how far we've gone. If we get Telecom Italia and Zayo start rejecting these invalids as well, I would expect to see that distribution to shift even farther to the left. But this is progress. And if you don't believe me, there was this incident in Orange, España last month where we had a hacker stumble upon the login credentials to the RIPE NCC portal, and they decided to log in and just this is a kind of an act of vandalism here, just to mess with their account. And they knew enough to know, well, if I create some ROAs that don't match how things are routed, then it'll trigger our security system to essentially attack itself. This is kind of an autoimmune response here where it would start rejecting these routes. And so that's what ended up happening. There was no traffic that was misdirected despite some poorly worded news coverage. No data was compromised, but the networks became unreachable as a result of this. I used Job Snyder's RPI views tool to go back in time and reconstruct the steps that this person took. It really were these 4 rows that were created that caused the most havoc. And this dip here in this graph on the bottom is the dip in propagation as a new problematic row gets propagated out through the internet, and we see a dip in the propagation of the BGP route, not the ROA. And when these routes are not available, then they can't communicate. So if you didn't believe, this couldn't have happened if we didn't have a lot of networks rejecting invalids. And I'd say that's not just RPKI, because some of that stuff is fairly recent developments, I would say, and things that were improving even before this recent stuff with RPKI. And not all of these problems can be solved with RPKI. I would just say that in general, it's hard to put it to enumerate the issue, all the different types of things that contribute to this, but there's a general improvement in route hygiene, I would argue. And we have like IRR filtering, there's just a higher level of expectation, a higher level of awareness. I'd like to think some of the stuff I've written over the years maybe contributed to that. I would just point out also that for a few years there, China Telecom was kind of the boogeyman in this space. They were involved in a bunch of leaks. I was the author of some of that stuff. But in 2020, they joined Manners, committed to cleaning up the routing, and they do not appear in any leaks. Leaks still happen, but they're not. China Telecom is not involved. I wrote this tweet here. I was like, "Hey, congratulations! I'm looking forward to this benefiting everybody." I got a nice reply back. I assume they didn't like me, but maybe that's maybe I was wrong about that. But anyway, it's another kind of unheralded good news story here of like another problem we don't seem to have as much anymore. Again, just to sum up the RPKI portion, I think the two takeaways I'd like people to have is that the majority of traffic, if we buy this analysis, the majority of traffic is directed to RPKI valid routes. That ought to be incentive for you to be rejecting invalids for your network and your customers' networks, because that's going to protect how you egress traffic. You're not going to get tricked by a leak. You're not going to misdirect your traffic. So we talk a lot about some of this is beneficial for the broader internet, but you've got something to gain from that as well. And then conversely, because we're seeing this route propagation drop by a half or more when a route becomes invalid, that's incentive to create the ROAs so that the rest of the internet can, in an automated fashion, look out on your behalf, like the internet did for Twitter when this one provider leaked out this hijacked route. That's the motivation for RPKI. But obviously, everything I've been talking about so far has been mostly accidental stuff, or intentional plus accidental. Obviously, we know that there's been some cases here that people have intentionally gone after routing stuff. Here's a couple photos of people doing that. And so I'll just talk about a couple of incidents. We had, I think in this space, an important moment was this Black Hat talk of Bielosov Capella talking about using BGP to do a man in the middle. A few years later, myself and my colleagues at Renesas, we identified what we felt like was the first man-in-the-middle BGP attack found in the wild. We had routes hijacks coming out of Belarus, targeting Visa and MasterCard and various governments over a span of a few weeks, using BGP communities to cleverly shape the propagation to ensure the man-in-the-middle would be successful. But these days, the space where we see this is in hijacks involved in sophisticated attacks targeting cryptocurrencies. I won't go through EtherWallet and Clay Swap, but those are also important ones to understand. I'll just mention a little bit about the Stellar Bridge case. And honestly, there's more of these cases going on that not all of these have been public. But the Stellar Bridge, this is a service to convert between cryptocurrencies. The attacker picked the biggest kid in the playground to go after and was unfazed by going and hijacking AWS stuff. You think of a company that's probably has enough resources and wherewithal to defend themselves. These guys were undaunted. They knew they could get away with what they were going to do. So why was this successful? For a couple reasons. For one, these guys were smart enough to know that they needed to get a data center that would announce these routes and announce routes that they would allow them to forge an AS path where they would be able to circumvent any ROV protection, because the address space they're going after was going to have a ROA. They also needed to know that the upstream of that hosting provider had built their automated filtering based on IRR data they could inject a bad route object into. So they were able to put this object into AltDB, this free RIR alternative, and have that appear in Aurelion's filtering that would allow QuickHost in the UK to announce AWS address space, something it shouldn't normally be able to do. And then they were forging AS paths, and these routes were getting out into the internet. So in this graph I put out at the time, you were like these 4 pulses where they were announcing and withdrawing, announcing, withdrawing over the span of a couple of hours. During each of these, they're running their attacks and stealing cryptocurrency. Eventually, AWS catches on, and they announce the same /24, but it's too late. The attack is already over. And so in the aftermath of this, I think it's important to understand, when we talk about RPK ROV, this is something that's going to help us most in those bonehead error end of the spectrum, and it's going to help us a little bit on the other side. But this was an actor that knew how to step around that mechanism. And my critique here was that these the ROAs they had created, we got some pushback from AWS on this, but these are pretty liberal. These are the ROAs allow routes in the ranges from /10 to 24. 3 different ASs could announce it. So that gave, in my opinion, the attacker a lot of room to work with to manufacture something, a route that would be believable, would survive the IR-based filtering, the RPK ROV, and enable them to do their attack. And and in the end, we need something, like BGPsec to completely eliminate this impersonation of ASs. Obviously, there's lots of critiques around BGPsec, and we don't have to debate the whole thing here. One of those is that we've got it's only as good as this contiguous set of BGP-aware ASs. I would make the case that in this scenario, that is not such a problem, because if Aurelion and AWS were both BGPsec aware, Aurelion would have preferred the route from AWS over QuickHost that wouldn't be signed. So I think that would have benefited the entire rest of the internet, even if the rest of the internet was not BGPsec aware. So I would argue, and you can debate me on this, that there's benefits from partial deployment here as well. But like I said, we've made a bunch of progress. There's things we still need to do. We're working our way up that spectrum. We've got ASPA now getting rolled out that will help with those adjacency leaks we talked about at the beginning. RPKI, I think, there's a lot of benefit, and I can give you offline some more examples of where it's helping on a regular basis. And then we need some sort of a mechanism to address this origin impersonation, because that's going to continue to cause us problems. And I guess I take a glass half full view of this, that in my almost 15 years of writing about this stuff, I'd say that the needle is moving in the right direction. This is just a really hard problem. We have to keep working at it. I appreciate all the folks that attend this conference that have been a part of the solution and trying to improve routing security for your networks. And thank you for your time.
Thank you very much. Do we have any comments or questions? Yeah, we had so many incidents. Thank you very much for sharing.
Okay.
Thank you very much. So, last but not least, we have Thomas Holterbach. Oh, yeah, he's coming. From University of Strasbourg. He will talk about hijacks.
Yes.
For the viewers.
Okay, can you hear me? Yes, I think it works. So hello everyone. I am Thomas Holterbach from the University of Strasbourg in France. And today I will talk about forge origin hijacks. Actually, the previous presentation was a great transition to this presentation, because Doug mentioned some hijacks, some attacks that were actually successful, and they used forge origin hijacks. So now I will show you how we can detect those hijacks. But let's start with a very simple example. We take a few autonomous systems that are connected using peer-to-peer or customer-to-provider relationships. And then we assume that AS7 in green announces a prefix that it owns, 7/8. So a BGP route will propagate through the network, and the other autonomous system will be able to reach that destination using an AS path, and the traffic is supposed to follow this AS path. Okay. So now imagine that there is an attacker, AS5, who actually hijacks this prefix, 7/8, So the hijack route will propagate, and some of the autonomous system here, 1, 3, and 6, will divert the traffic to the attacker. Okay, so you probably know about BGP hijacks already. And you probably know that there are defenses against hijacks as well. So typically there are protocol extensions such as API plus LOV, BGP-sec, ASPA, they were mentioned before. There are configuration guidelines such as route filters, mentioned before as well. And there are monitoring platforms such as Artemis and BGP Alerter, which can detect hijacks in near real time. Okay? The problem is that this is very useful, but today, BGP is still vulnerable to forged origin hijacks. Okay, so what is a forged origin hijacks? It's a hijack where the attacker prepends the valid origin in the AES path. Okay, so from a BGP standpoint, the hijack route actually appears legitimate. Okay, so here, for instance, this is what happens in this case. IS5, the attacker prepends 7, the legitimate autonomous system here, and the hijack route will propagate. The drawback of a forged origin hijack is that the AES path is a bit longer, so it will propagate less, but the attack will still be successful. In this case, for instance, still 2 autonomous systems, 1 and 3, divert the traffic to the attacker. And unfortunately, the existing defenses, they actually poorly neutralize those forged origin hijacks. Okay, so RPKI plus LOV, they cannot detect forged origin hijacks because the origin is actually valid. BGP-sec ASPA, it will take a lot of time to be widely deployed. Route filters, they are often missing or inaccurate because we are still seeing a lot of hijacks every day. And finally, monitoring platforms such as Artemis and BGP Alerter, they are useful. They could detect them, but they could only detect them for the hijacks that pertain to the AES that deploy the system, okay? So it's kind of narrowly focused. And the problem is that, as it was mentioned in the previous presentation, forged origin hijacks, they are actively used by attackers, okay? So those are just the 2 examples that Doug mentioned before, 2 attacks that targeted crypto exchange platforms and that were successful because in both cases, the attacker managed to steal cryptocurrencies. Okay, so today, I want to introduce you a system which is called DIFO, and it's a system that can detect forged origin hijacks on the entire internet, okay? So the outline of this presentation, first, I will show you what's the main challenge that we need to solve. Then I will explain you DIFO's inference pipeline. Then I will show that the inferences are accurate. And finally, I will show that DIFO is up and running and that you can start to use it today. Okay, so the main challenge of DIFO is to detect fake AES links. Okay, so why is this the main challenge? Because imagine we have the scenario that I described before. We have BGP vantage points, the one from recent route views, so we can see BGP routes. And then when we look at the AES path, we will see that 5 and 7 here, they are actually directly connected. They appear directly connected when we look at the AES path, right? But this is actually a fake link. This link does not exist. 5, 7, they are not directly connected. They are not pairing directly together, okay? And this is a sign of a forged origin hijack. Okay, so why it's a sign that we are using in DIFO to detect hijacks? Because an attacker can actually hardly escape from creating a fake link when it launches the attack. Why is that? Because an attacker could prepend actually not just the valid origin in the AES path, but could prepend an entire path that exists in the topology. For instance, here the attacker could prepend 6 and 7, in which case the hijack route would have 5, 6, 7 consecutively in the AES path, which is a path that exists in the topology, so there would be no fake link in this case. But the problem is that the AES path would then be longer, and the hijack would propagate less. In this case, actually, none of the autonomous system would divert the traffic to the attacker, so the attack would be unsuccessful. Okay, so this is great. Let's focus on fake links. The problem, though, is that we took BGP routes collected by RIS and route views, and we found that there are a lot of new links that appear every day, 166 in the median case. And some of them might be fake, but probably the vast majority of them are legitimate, okay? So the goal of DIFO is to be able to know which one of those links are fake and which one are the real ones, the legitimate ones, okay? And to do that, we use an inference pipeline that I'm going to describe to you now. And really, this inference pipeline is tailored to discriminate fake AS links from the real ones, okay? Okay, so the inference pipeline comprises 3 steps. First, DIFO needs to find new AS links. So to do that, we take the RIS route views vantage point, we look at the AS path, we build the AS topology, we maintain it over time, and we look for new AS links. For instance, here we have 3 new AS links, and one of them is fake. Okay? Then for each new AS link, we compute feature values. And here we have 4 categories of features. Okay? First, we have the topological features. So here, I don't have the time to explain you in detail how they work, but in essence, the intuition is that the AS topology follows a strong hierarchical pattern. Okay? There are a few autonomous systems at the top, many autonomous systems at the bottom. Okay? So when a new link appears, if this link breaks that structure, it's a sign that it is a fake link. Okay? For instance, if a stub AS suddenly becomes central node in topology, it's a sign that something weird is going on. Okay? So we have different topological features that capture different sort of changes, and we use this feature in our inference. Then we have the peeling DB features. Okay? So here, DIFO actually takes information from peeling DB, such as the country or which IXP the 2 autonomous systems they peer with, or in which facility they are present. And then we compare them, and if the 2 ACs that became connected, they do not share any peering information, for instance, if they are in different countries, if they do not share any IXP or any facility, it's a sign that they are not supposed to be directly connected and that the link is actually fake. Okay? So we also use this information in the inference. Okay, then we have the AS path pattern feature. Here, DIFO not only looks at the new link, but it looks at the entire AS path that includes the new link. Okay? And here we know that the ASs, they are supposed to follow some business relationship that are typically based on the Garo-Wexford model. So when we look at the AS path, we are supposed to see some patterns. For instance, when we look at the AS degree here on the y-axis, when we have a path between 2 stubs, we are supposed to see that the degree increases and then decreases, right? That's the typical pattern that we are supposed to see. For a core 2-stub path, we will see that the degree decreases because first we have the tier 1, for instance, with a very high degree, and then we go to the stub, so the degree decreases. So those 2 patterns, they are legitimate patterns, okay? However, if we see something like this is very weird. This could typically happen when a stub hijacks a core AS. So for instance, in this case, the origin is the valid one, is the victim AS number. So it has a high degree because the victim is a core AS. And then the second AS has a very low degree, it's the attacker, it's a stub. And then we see a normal pattern, it increases, decreases. But overall, this pattern is very weird, it's very suspicious, and DIFO uses this information as well in the inference. And then we have a last feature, which is the bidirectionality feature. I'm not going into the detail here, but basically, an attacker cannot fake both directions of a link. So if we see that a new link is observed in both directions, it is very likely legitimate. An attacker cannot fake both directions because otherwise there would be a loop in the AS path, and that's not possible. So we use this as well in our inference. Okay, actually those 4 features, they are the key ingredient number 1 in the inference pipeline. Okay, why it's a key ingredient? Because they are complementary, okay? There are many attack scenarios that are possible in the internet, but here we ensure that regardless of the attack scenario, at least one of those features will be useful for the inference, okay? So they compensate each other, and they are complementary, and this is why it's a key ingredient in the inference pipeline. Okay, so then the last step is to infer hijacks. Okay, so here we actually follow the typical approach that is used for link prediction frameworks. Okay, so we sample a set of existing links and a set of links that do not exist. Okay, so those are the positive and the negative cases in a sense. Okay, we compute feature values for those sampled links, and then we train an inference model. Here we just use a random forest. And then we use this random forest to make inferences. The problem, however, is that if we naively follow what is done in the literature, it will not work well in our case. Why it's not going to work well? Because again, the AS topology typically exhibits a very strong hierarchical pattern with a few autonomous systems at the top, many stubs at the bottom, okay? So when we randomly sample links, we will end up with many stub-to-stub links and only a few core-to-core links, okay? So just for this to be visually speaking, what we did is we clustered the autonomous system in different categories based on their degree and their customer count size, okay? And then we sampled randomly a set of non-existent links, okay? And this is what you observe. We observe that 98% of the links that we sample, they are between two stub autonomous systems, okay? So this means that if we train DFO on those links, it will work very well for attack scenarios that involve two stubs, but it will perform very poorly for other attack scenarios, okay? So here is where we actually plug in our second key ingredient, which is a balanced sampling scheme. We ensure to sample all types of links so that we cover all possible attack scenarios, okay? Okay, so now I will actually show you that the inferences are in fact accurate in all attack scenarios. It's a bit tricky to evaluate DFO because there is no grain truth, okay? Except the two cases that I mentioned before. We don't know any other forged origin hijack. So what we did is we artificially created forged origin hijacks. So we took existing AS paths and we just added a new origin, which creates a new AS link. And in some cases, the AS link that we create actually is not true. It exists in the topology, so it's a positive case. This AS link already exists. In some cases, we add a new link that actually does not exist in the topology, so this is a fake link, so it's a negative case. And then we can use those artificially created forged origin hijacks to evaluate the true positive rate of DFO and the false positive rate of DFO, which are the two metrics that we usually use to evaluate a classification algorithm. Okay, so here are the results about the true positive rate. So on the x-axis, you have the type of the autonomous system of the victim, and on the y-axis, you have the type of the autonomous system of the attacker. And basically here you can see that regardless of the attack scenario, so regardless of who is the attacker, who is the victim, there is always a high TPR, okay? Actually, the lowest TPR is 0.73, which is still quite high. In terms of false positive rate, again, regardless of the attack scenario, so regardless of who is the attacker, who is the victim, the false positive rate is always very low. Actually, the maximum FPR is 0.15, which is still rather low. Okay, so finally, I will show you that DFO is up and running, useful for operators, and that you can actually start to use it today. So to see whether DFO is actually useful for operators, we're interested in the number of cases that it actually reports, okay? Why? Because if we use a very naive approach, such as just reporting all the new AS links that exist, which is a kind of the state of the art today, we would end up with many reported cases, okay? This is what we see on this graph. We would end up with thousands of cases reported every month, okay? And this is too many. We cannot manually investigate them, okay? But if we use DIFO, you can see that we really greatly reduce this number. So now we have just a few tens of cases that we need to investigate, and this is for the entire internet, right? So this is not a lot of cases. Actually, I will demonstrate you now that, in fact, we can manually investigate those cases. Because DIFO is up and running at this URL, so you can access the website. We provide the paper, because we will present this at NSDI in April. The presentation as well, the source code if you're interested. And now, to conclude, I would like to demonstrate you that DIFO can be useful. And here, I will actually use the AppNix prefix and ISN. Okay, so when you go to the website, we actually provide all the reported suspicious cases, and you can filter them. Okay, so for instance, what we did is we wanted only to see the suspicious cases for which the victim is 4608, which is AppNix ISN. And then we took a large period of time, so 2 years, 2022, 2023. Okay, and here are the suspicious cases that we see. So there are only 3 suspicious cases, so not a lot. We could manually investigate them. That's what we did, we manually investigated. And we found that this first suspicious case is actually very weird. Okay, so if you click on the line here, you can actually see the AS pass that is inferred as suspicious. And this AS pass, sorry, not AS pass, this BGP route, this BGP route that is suspicious. And if you look at this BGP route, you can see it's for the AppNix prefix, 103.0.0.0/16. You can see the AS pass. The origin is AppNix ISN. But if you look at the other IS number in this AS pass, you will see something weird, actually. So you see that basically between the AppNix ISN and SecureBit, which is a BGP tunnel broker, there is a stub autonomous system with not a lot of information on PeeringDB, so we don't really know what it does. But here it seems that it sort of provides transit between SecureBit and AppNix ISN, which doesn't really make sense. So I think this case, for instance, is useful for an AppNix operator, so they could check this case, investigate, and take countermeasures if necessary. Okay, so that concludes my presentation. So today I presented you DIFO, a system that detects forward-routing hijacks. So DIFO runs in a commodity server. It can detect hijacked on the entire internet. It is accurate in every attack scenario. It can detect past hijack. It also works in near real-time detection, but this feature is not activated yet. We will activate it for NSDI in April. And finally, DIFO is robust against adversarial inputs. I didn't have the time to talk about that, but if you're interested, you can also look at the paper, which is on the website. Thank you very much.
Thank you very much. Great. So there was some suspicious announcement on.
Yeah.
Wow.
Actually, we found many other suspicious cases, but I cannot show all of them. But the best is just that you put your SN and see if there is something weird.
Okay, so we can try by ourselves.
Of course, there is. You can try by yourself.
Any question, comment? Yes, please. State your name and affiliation, please.
I can do that. Hi, this is Robert from Drive NCC. Maybe only for the educational value. So you said you can find events that happened or are happening to your network, active attack or so. And then you take countermeasures. So suppose that I'm an operator. What do I do? What are the countermeasures?
Well, I guess it depends on the case. I think you can advertise more specific prefixes, for instance, or that's one option. I think this goes a bit outside of this word specifically. Yeah, so I guess it depends on the case. So you investigate. First of all, you check if the traffic was indeed diverted to the attacker or not, because sometimes maybe it might be a misconfiguration. For instance, in the case that I showed, it could be a misconfiguration, in which case perhaps I think that what happened in this case is that the route didn't propagate further because probably SecureBit filtered that route. So in this case, you can maybe just send an email to the possible AS that did a misconfiguration. You just tell him to fix the
Notify the
misconfiguration,
attacker that I
right?
see them, right?
If the hijack actually diverted the traffic and it is an attack, a malicious attack, then you have to take more like strong countermeasure, advertising more specific prefixes, making sure that the filters are accurate, contacting your provider to make sure that the filters are accurate, things like this. But again, it depends on the...
Right, thank you. Then the other question is, what is the relation between DIFO and BGP-SAC and or ASPA? So in the future, let's assume that at least one of those will be widely deployed. Is that going to be more useful for this work, or this work is going to be more useful for the deployment of ASPA and
If ASPA or BGP-SEC are fully deployed, I don't think you need this anymore.
I guess that's good news.
That's, well, because there is this big if, right? And I think we are far from being there. So what will probably happen in the near future is that we will have a transition towards BGP-SEC and ASPA. So we will have a sort of a partial deployment. So when we can use ASPA, for some of the links, we might be able to use it because the operator, they are using it. So if we can use it, we should use ASPA because ASPA is, and BGP-SEC, they are cryptographically based, so it's deterministic, so we can be sure that there is no false positive, no false negative. So we should use them, but if we cannot use them, then it's an alternative. We can fall back to a probabilistic technique such as DIFO. So that's how I would see it in the future.
Thank you.
Hi, Thomas. I'm Vaibhav from Hatzplatten Institute in Germany. And so my question is, how much does this actually help solve the problem, or does it actually shift the problem from one place to another? Because if you consider the fact that you're assuming that the inference model is benign, right? If I were an attacker, and if the system is deployed, I would actually spend all my energy into poisoning your inference model itself so that your model cannot detect attacks, right? So
yeah.
While it's a very good academic exercise, I'm just wondering, don't you think it would be better time investment into deploying BGP-SEC instead?
Well, so first of all, I think you are mentioning possible adversarial inputs, and this is a very good point. Actually, if you look at the paper, we have a section about adversarial inputs, and I didn't really go into the detail because I only had 20 minutes, but each part of our algorithm is designed to prevent adversarial inputs. Of course, it's not bulletproof, and probably you can find cases in which you can maybe still trick the system, right? But originally, we had this in mind, so we tried to be robust against adversarial inputs. So now, why is it useful? Well, it is useful, first of all, because you can quickly see whether you are being under attack or not. It is also useful to go back in the past, in the history, and check, because now we only know about 2 forward-joining hijacks, that's only what we have in the news so far. Maybe there are more that happened in the past and we don't know. Maybe those 2 are the only one that happened. Maybe there are like 10, 20, 100 other attacks that we just don't know about them. So now with DIFO, we can go back to the history and check and study them. I mean, I'm from the research side, so this is useful for researchers, for instance, maybe not for operators, but at least for researchers, it gives us some meat, so that can be useful for this. But generally speaking, I think there is still more to do. That's the first step. Of course, now we need to improve the system even more. I think there is still room for improvement, and one option clearly is to go towards looking at the data traffic as well, combining the two, and that will make the system even more robust, actually.
Good morning to all. I am Zahir from Sri Lanka. So, could you please explain me what is the mechanism used for the detections? So, is it like a machine learning algorithm or kind of?
It's a kind of, in fact, machine learning algorithm, but it's not crazy machine learning. There is no neural network, deep learning, blah, blah, blah. It's a random forest, so it's very basic. But what matters in this machine learning part is our sampling, right? It's the key ingredient number 2. This is the key part. Then the machine learning model that you use, it doesn't really matter. You can use a tree, random forest, neural nets. That's not very important. What matters is that we manage to tailor the learning part so that it works well for detecting forward-joining hijacks, right?
So my question is it one algorithm is enough for the detection? So without the accuracy?
Yeah.
So if you are not using the separate algorithms.
You mean if you are not using our sampling scheme?
Yeah,
right?
that's good.
Yeah, if you are not using the sampling scheme, it will perform very well for attacks that involve 2 stubs,
yes,
but it will perform very poorly for all other attack scenarios. So if you just compute a true positive rate, it will be very low. So I can maybe go back here, for instance. It will be very high for step to step. So on the top left corner, we will be close to 1, the best possible score. But for all the other cases, it will be very low. Okay, so this is, if you just apply existing algorithm that exists in the literature, that's what you will see. Right. But if we use default, it works everywhere for every attack scenario.
Thank you, interesting.
No problem.
Okay, no other questions. But yeah, probably we will have more partial hijacks in the internet. So for that, we need more monitoring, and for that, we need more vantage point. Because BGP is good at hiding, right?
That's, well, actually, we're working on that currently, so that's the next step.
Okay.
Having more vantage points, yep. Cool, thank you.
Again, thank you very much.
Thank you.
So this concludes our Apops session today. But before concluding, I have several announcements. Again, we have a lightning talk session on this Friday, so the submission is still open. So you have some idea or story to be shared for this community, like a 5-minute talk. Please submit your slide to the Apricot website. And also, we have an experimental Wi-Fi network here, Apricot-V6 only. It's a V6 only. And if your client supports the V6 only network, like iOS or Mac OS, your computer automatically configure extract functionality on your interface. It's interesting to see. So if we want to try Apricot V6 only network, it has the same SSID, same password as a wireless. So you can connect to this experimental Wi-Fi environment as well. And one more, we have a peering meetup somewhere in this for Gallery 1, I guess, Philip? So where's the room for the peering? Gallery 1 is over there. So if you have an appointment with your partner, it's over there. So that's all from my side. Thank you for joining us today, and see you next time. Thank you very much.